Welcome to today's Explainer. We are jumping right into a totally fascinating shift happening in the world of engineering right now. You know, for years we've built our flying machines out of highly rigid materials, stuff like carbon fiber and hard plastics. But today, we're looking at how biology is inspiring a massive, fundamental shift. We're moving away from those rigid, often dangerous flying machines and moving towards soft, highly adaptive drone companions. And the absolute secret weapon driving this whole revolution? It's all about inflatable silicone air sacs. To really understand why this shift is such a big deal, just think about the drones we're all used to seeing today. They fly incredibly fast, they hit the brakes at the absolute last second, and they rely on these demanding, millimeter-perfect control loops just to stay in the air. But what happens if there's a miscalculation? Say, a sudden gust of wind, a tiny sensor glitch, or just plain old human error? Well, it leads to a very hard, brittle impact. Essentially, these rigid drones have this kamikaze-like flight style. They act a lot like flying blenders, which, as you can imagine, makes them pretty dangerous to operate around people or in fragile environments. So here is our roadmap for today's Explainer. We're covering 1. Pufferfish bumpers, 2. Bird-inspired perching, 3. Octopus arms, 4. Valve manifold logic, and 5. The soft future. Let's get right into it. This comparison perfectly captures the core paradigm shift we're exploring today. With rigid drones, absolute perfection is demanded from the software, and when they inevitably fail, it's a catastrophic, brittle failure. But on the other hand, we have soft drones. By integrating these flexible, inflatable pneumatic chambers made from silicone elastomers, we're building structures that actually forgive mistakes. If a soft drone hits an obstacle, it doesn't shatter. It experiences a graceful failure. It literally absorbs the error, keeping itself and its surroundings totally safe. Section 1. Pufferfish bumpers for safety. So to protect the drone and us, engineers are actually looking at the pufferfish for inspiration. Drones can now be equipped with a rin or a cage of silicone air sacs right around their frame and propellers. Now, during normal flight, these sacs are totally deflated, which keeps the drone compact and aerodynamic. But when things go wrong, they inflate, acting just like a crumple zone in a car. By creating this soft, inflatable buffer, the drone can literally bounce off humans, animals, or tree branches. Instead of causing deep cuts or shattering its expensive carbon frame, those impact forces get spread out over a much larger, softer area. It's actually really similar to those inflatable protective packaging bags you see in shipping boxes, or even Michelin's inflatable drone arena concepts. Now, what's really fascinating here is the automated safety logic behind all this. I mean, how does a drone actually know when it's time to go full pufferfish? Well, proximity sensors, things like vision, LiDAR, or ultrasonic sensors, are constantly watching to see if a person or an object enters the danger zone. Or let's say the drone is suddenly buffeted by a huge external wind gust or accidentally pushed by a person. Its internal measurement unit instantly detects those unexpected accelerations, and bam, the drone's defensive logic kicks right in. It reduces the throttle, starts descending safely, and immediately inflates those bumpers. You are literally giving the drone an extra physical margin of error, turning a potentially dangerous hazard into a totally harmless soft bump. Moving on to Section 2. Bird-inspired perching. This mechanism completely flips how we think about landing. Instead of those ultra-precise, high-speed slam landings we're used to, designers are deliberately trading a little bit of top-speed performance to gain massive safety benefits. Imagine a drone approaching a tree branch or an industrial pipe. Instead of having to hover perfectly next to it, the drone has rigid metallic or wooden legs, very much like a bird, but attached to these legs are inflatable silicone sacs. As the drone makes its approach, it partially inflates these sacs to intentionally create aerodynamic drag. That slows it down naturally without needing massive battery-draining reverse thrust. Then, the second it makes contact, the bulbous sacs at its feet fully inflate. This creates a grippy, padded talon that safely decelerates the drone and conforms perfectly to whatever surface it's landing on. And here is the real so what of it all, the huge difference in energy and stability. Think about a standard drone inspecting a bridge or a wind turbine. It has to hover, right? That drains a massive amount of energy, creates a super loud buzzing noise, and leaves the drone completely vulnerable to wind gusts. But by using these soft, inflatable claws to perch on irregular structures, the energy use drops to near zero. The air pump just turns off and the valves simply hold the pressure. The drone goes totally silent and its physical stability is incredibly high. It completely unlocks the ability for delicate, sustained observation of the environment. All right, Section 3. Octopus arms for delicate objects.
If we want these machines to physically grasp the real world without destroying it, the octopus is the absolute perfect model. Drones are being used more and more in agriculture, but traditional, rigid robotic claws will easily crush or bruise a fragile harvest. So, by replacing hard claws with inflatable silicone tubes, which are basically soft pneumatic artificial muscles, the drone can gently wrap around completely irregular shapes, whether it's an apple, a delicate peach, or a ripe tomato. The soft fingers distribute the pressure perfectly evenly. You use low pressure to make initial contact and slightly higher pressure to secure the fruit, keeping the grip well below the threshold that would cause a bruise. Plus, inside the payload bay itself, small inflatable cells act as internal cushioning. They dampen all those high-frequency flight vibrations so the cargo doesn't get damaged in transit. It's brilliant.
Which brings us to Section 4, how valve manifold logic works. So you might be wondering, how on earth do we control 4 independent robotic octopus arms without strapping heavy, battery-draining air pumps all over the drone? I mean, you absolutely cannot put 4 heavy air compressors on a tiny flying robot. Well, the secret is the valve manifold. You start with one single lightweight pressure source, like a tiny pump or a pressurized tank. That feeds directly into the valve manifold, which acts just like a pneumatic switchboard. It takes that one single pressure input and branches it out into multiple outputs, one for each arm. Each output has its own tiny fill valve to let air in and an exhaust valve to release air back into the atmosphere. And this is where the real magic happens, using something called time multiplex control. Because these silicone sacs naturally hold pressure once they're sealed, you don't actually need to pump air continuously. You can just briefly open the valve for arm 1, letting it inflate just a little bit. Then you close it, trapping that air. Next, you open the valve for arm 2, and so on. A super simple microcontroller can rapidly cycle through these valves, effectively painting pressure into each arm sequentially. This clever little trick allows a drone to perform incredibly complex reaching, grasping, and releasing motions with 4 distinct limbs, all while running off just a single tiny air source. Finally, Section 5, the soft future. Stepping back from the nuts and bolts for a second, what biology is really teaching us here is that morphology, the actual physical shape and squishiness of a body, does half the heavy lifting for you when it comes to control. In this new engineering paradigm, we still use hard parts like metal struts or carbon tubes because they're great at handling the load-bearing and macro precision, but we let the soft, inflatable parts manage all the unpredictable contact and adaptation. An air-backed structure just naturally absorbs a random gust of wind, a slightly misaligned landing, or bumping human, all without needing thousands of lines of perfect code or hyper-fast sensor reflexes. Mistakes don't equal disaster anymore. They just result in a soft sag or a gentle bounce, a graceful failure rather than a brittle catastrophe. As we wrap up today's explainer, I really want to leave you with this final thought. By implementing these inflatable pufferfish bumpers, perching bird legs, and soft octopus arms, engineers are doing way more than just slapping safety guards on a machine. We're literally giving these drones a soft, adaptive anatomy. They can morph, they react naturally to wind, they grasp fragile things gently, and they fundamentally forgive the physical mistakes of the real world. So consider this. By blurring the lines between living anatomy and machine engineering, are we just building better tools, or are we fundamentally bringing our technology closer to life?